I know I asked people to look at something. I don't know if you did or not, but I'm going to go through this, and this is not in the book, but you need to take good notes. I'll post things. How many actually looked at what I posted? In there, if you had me for signals and systems, you recognize a lot of that. All right. If you haven't, be real attentive here, and I will discuss this. Now, with real EMC, the reason this is important, most of the analysis is in the frequency domain, and the tools you use are called network analyzers or spectrum analyzer. And what they do is show you a voltage, typically versus, and it's usually in dB, versus frequency. And what I'm going to do here is do the same type of analysis the same type of analysis that would be pertinent to these measurements. So this is important. This is really EMC stuff. In Wentworth's book, he just talks about one thing, rise time. He talks about a square wave with a given rise time and says that the bandwidth is about 1 over tau, with tau being the rise time. Well, that doesn't say nearly enough about this important issue. So I'm going to go through it. Please be attentive here. This is not something that's trivial. If you've had it before, you probably can relax a little bit. So in general, last time I said not this again. These are brand new markers, by the way. I don't know. They may have been very old or something. Oh, that one's even worse. I got a feeling this isn't going to go well. Let's get rid of that one. There's got to be one of these things that works, surely. Just give me a second. All right, that one we can work with. Let's try this one. And we'll try that one and this one. Maybe. All right. So, nope. All right. Back to square one. When we're taking a look at a signal, this can represent anything. Usually it's voltage. When we have x of t here, and we have a signal where there's a certain rise time, this is called t rise, or tau rise. There's going to be a time it stays on, then it's going to fall down. This will be the fall time. The magnitude of the height of this waveform is a, really, right there. And I'm going to just say t rise is equal to t fall. And the way you select this is find the one that's shorter and use it. In other words, you always do worst case analysis. This waveform repeats itself. This is versus time. This is going to be the period t. And then it repeats itself. And everybody can get an appreciation for this. This is just a square wave, x of t. Typically, that indicates a voltage. Most of the time, you don't talk about current here. All right, now with that one, I said because it is periodic, and here I'm going to do it over here, I can say that this waveform, x of t, can be given as a Fourier series. I'm going to use the exponential Fourier series for a very important reason. Please listen to me. So x of t generally is equal to the summation of n equals minus infinity to infinity of c of n times e to the jn omega naught t. That value c of n is given by 1 over t. The integral, and really down here, it's at any point. Doesn't matter as long as the point here is 1 period long in length, all right? So you can say from epsilon to epsilon plus t. And you pick out epsilon so that you don't actually land on a transitional point where there's a delta function. You always adjust the window where you have integration. This is going to be x of t times e to the minus j n omega naught t dt. And I'll try to erase some of the stuff that's up here. All right. Now that's true. You've all remembered this, right? Yeah.
What's the symbol next to the summation of e to n?
This is just c of n, right? And this is c of n. These two are the same. Do you all remember? This is exponential. I'm sorry about that. Yeah, just yell at me if that's bothering you. What we're talking about here is really just doing an exponential Fourier series. We could do a sine and cosine, but that is the worst way to do these problems. I'm going to tell you that. It's more work than it's worth. And you can get it because technically what? C of n here is going to have a magnitude and angle, right? If I want to put it in terms of sines and cosines, can I use Euler's identity there and just break it up into a sine and a cosine? So it defeats the purpose to talk about that. Now, that's what x of t is. If I take a derivative of this, it's going to be hard to fit this on here, but I hope you appreciate what I do. If I take a derivative of this, then I'm going to get a square wave here that's actually going to go out to this point. And the height of this would be a over tau rise. Then it's going to go to 0. And right here, I didn't put this in here, but the width of the pulse from the 50% point here to the 50% point here is actually tau. That's how it's done. All right? How many had me for signals and systems? All right. This is not going to be news to you, but it's a good review. If you haven't, now's the time to really be attentive, because this gets a little tricky. With the derivative, well, it's just really the slope of this line. It's rise over run. The rise is a, the run is tau rise. Comes down to here. The next point it triggers is right here. That's actually tau. And if you think about it, if this is the 50% point, you all see when I move this back, that point is actually tau right here. That's one of the advantages of doing that. They always have the width of that from the 50% on to 50% off point. They don't have it from here to here. Remember that, because that's never clear. It never, I mean, it's very hard to tell exactly where that is. These are actually a little bit, frankly, this waveform right here is a bit curved, and this one looks like a shark fin only stretched, if that makes sense to you. Now, here it goes negative, and then it goes to 0, and it repeats itself, all right? It's going to repeat itself. Is everybody clear on that? Now, that value is a derivative with respect to time. If you look here, when you take a derivative with respect to time, you have x prime of t equal to same summation, but now I'm going to have the c of n value only times j n omega naught. Still, the summation goes from minus infinity to infinity, and then it's e to the j n omega naught t, right? Now, just for the record, to make sure you see this, you all see if you take a derivative of that with respect to t, t only appears in that exponential. When you take a derivative of e to the at dt, it just brings out the constant a, and a in this case is j n omega naught. You all see that? Make sure you do. If you didn't get a good thumping in signals and systems on this, now is the time to really focus, because you're going to use what I'm showing you, not just EMC and radar, you're going to use it in a lot of courses. And I can only tell you that I have had kids in my radar class that really were clueless about Z-transforms and some of these things, and it made me shudder, because if you're out there and doing radar work or EMC work, if you don't know these transform properties basically down, you're not going to know every transform, but you know the trends, you're just in a world of hurt. You won't be able to do anything effectively. Now, this is the one thing that is important. That's a constant. Do you all agree with me? Remember, omega naught, I didn't put this down, but the actual fundamental frequency, F naught, is 1 over t, and omega naught is simply 2 pi F naught, or it's 2 pi over t. Most of you remember something to that effect. But remember, you always get the period, and that's the fundamental frequency. Fundamental is always critical. Now, since that's a constant, we can call this Cn of prime. Do you all agree with that? It's just a constant. I can replace it. The reason I'm replacing it is if that is a constant, then it replicates that form right here, and I can get that constant, which has a j and omega naught in it, over here. And I can say now my Cn prime would be still 1 over t. Now it's the integral from epsilon to epsilon plus t, but now it's x prime of t times e to the j n omega naught t dt. Do you all see what I'm doing here? That's a derivative, right? First derivative. My goal here for a reason I'll get to in a second is to get it down to just delta functions. And this is, yes, sir?
What is epsilon in this case?
Epsilon can be any, I use that as just a term where if I want to integrate over a period, right? Well, that epsilon, if epsilon is like negative t over 5, it would move it this way, right? I have to keep the window length of the integration the same. Wherever I start, I have to go. So I just use epsilon. Sometimes I just get tired of it, and I just put from minus t over 2 to t over 2, but I'm going to just leave it like that for now. Y'all agree that's for one derivative. Now, if you've had me before, you know what I'm going to do. I'm going to do another derivative until I get just delta functions, right? The next derivative does what? And if you haven't seen this before, be real attentive. Because this isn't stuff that I get more odd questions about this, mainly because people weren't attentive in class. When I take another derivative of this, and I'm going to try to keep this at this height right here. So I'm just going to show you. If I take another derivative, do you all agree this will be a delta function, right? This is going to be a delta function with a negative constant in front of it. This will be a delta function with a negative constant, and this will be a delta function. So I'll have only delta functions. Do we all agree with that? All right. I'm going to put it right here. This was x prime. Now I'm going to put x double prime down here. So y'all can see this, and I don't have to basically go down here and have people, stretching their necks. So here, it's a delta function. The height is going to be just a over tau rise. Do you agree with that? Now remember, that was a square well. It went from a over tau rise to 0. So this is going to be a negative delta function right here. It's going to have a negative trend. And its value is going to be minus a over tau rise. And it occurs at tau rise. And technically, you could write it delta of t minus tau rise, couldn't you? Because the delta function turns on where the argument is 0. So t minus tau rise turns that delta function on at tau rise, right? That's the way. I don't even put that in most of the time. Come over to here. Remember, that was something that right here, it has a negative slope, so the first derivative will have a negative square well, right? So this is going to have another negative value right here, and that negative value right there is going to have minus a over tau rise, over tau, pardon me, and it's really going to be times a delta. If I want to put a delta function there, I can put delta of t minus tau, right? And remember, there was a square well there. Now we're taking, negative square well. We're taking a derivative. Then at this point, this is going to be at the point tau plus tau rise. Now it goes positive to a over tau rise, and it's times delta of t minus the quantity tau plus tau rise. And that's what you're left with when you do two derivatives of x of t. And that's critical because almost all clocks, if the clocking speed is right and the rise time short, can be approximated like that. Almost all. I'm going to tell you that. Now I come over here and I do a double prime over here, and I'm going to say now my x double prime of t will actually be equal to the summation here from n equals minus infinity to infinity. I'm going to get another j and omega naught, right? Every time you take a derivative, you pull out a j and omega naught in front of that constant. So it's going to be a summation of c of n times j and omega naught squared. There was already 1. Two derivatives mean it's squared. If it was 3, it would be cubed, right? Then it's going to be times e to the j n omega naught t right here. And now this constant right here, I'm going to rewrite this one, is just going to become cn double prime. So this is the summation from n equals 0 to infinity, minus infinity to infinity right here, of now it's cn double prime e to the minus j n omega naught t. And here cn double prime is simply 1 over t times the integral from epsilon to epsilon plus t of x double prime of t times e to the j n omega naught t dt. I can tell you you'll start to appreciate how much this does for you in a little bit, the effect of it. So if we take two derivatives, we get this. Do you all see this? Let me make that as capital T so you see it. Now what I'm going to do, just for completeness, I'm going to go ahead. He is alive, right?
Probably.
There's a good chance, as long as he's breathing. I know. Well, if I'm doing my due diligence. We don't want death and dismemberment in this room. Anyway, well, now what I'm going to do is put x of double prime of t in terms of the delta functions. All right? All right, cn double prime is equal to 1 over t times the integral from epsilon to epsilon plus capital T. What are they going to be? Well, it's going to be a over tau rise. Just take a look at that. Then it's going to be delta of t, right? Then it's minus delta of t minus tau rise. Then it's minus delta of t minus tau. Then it's plus delta of t minus the quantity tau rise plus tau, right? It's all that. And actually, square block there. Then it's times e to the minus j and omega naught t dt. You can see I'm just putting in what the actual derivative is, right? I don't normally go through this length with talking to people in my radar class, but here I will, because I know a lot of you probably didn't see this. Not a lot, some of you in the back. If you hadn't had me, you haven't seen it. How many have not had me before in signals? Okay, well then you'd be real attentive here, because this is more difficult if you first time around. Now, what about a delta function you know? I've got to pause for a minute, come over here and just make sure everybody knows this. Delta functions have one property that we love mathematically. They sift through all the possible values of things in that they're multiplying. And if you integrate a delta function times anything, it extracts the value of the function at the point the delta function turns on. So if I have an integral from minus infinity to infinity of delta of t minus tau, and I have some f of t here, dt, well, that delta function turns on at tau. You agree with me? And that means it simply extracts the value of f of t at tau. Got me on that? So you get f of tau. And that's it. That's the big deal about this, because now I really don't do integrations. I just look where they turn on and evaluate the coefficient of the delta function, or whatever is multiplying the delta function, right? So please watch this. I come here, and now I can say that my Cn double prime is equal to, well, I'm going to get the A over T tau rise right out in front, because I know that's just constants, right? First delta function turns on at t equals 0. Agreed? Make sure you see it. If you haven't seen this for the first time, make sure you get this. Do y'all agree with that? Well, that means you evaluate this function over here when t is 0. And what is that value? 1. E to the 0 is 1. So it's going to be 1. Now, the second delta function turns on at where? Tau rise, right? So you come over here, it's multiplying this, and you evaluate this function when t is tau rise. And there's a minus sign, so it's e to the minus j and omega naught tau rise. The next one turns on at just tau, correct? It's got a minus sign. Now you evaluate this at t equals tau, correct, class? It's been a while for some of you since you've seen it, but it's probably making your memory, it's ringing your memory and you're getting it. Finally, this one turns on at the quantity tau plus tau rise, right? So we put that in there. So then it's a positive. So a plus e to the minus j and omega naught quantity tau plus tau rise. And then you put a bracket there. And that's my C of n double prime. I'm going to just do one thing here, and I'm going to tell you the trick. We want to turn these things into trigonometric functions ideally, because if we can do that, at least we know what they look like and how their behavior. What we're really going for after in a second is going to be turning these into sinc functions, because sinc have an envelope that is very unique. All right, so the first thing I'm going to do is say, I'm going to say that this Cn double prime, I can leave it as A capital T tau rise there. And then I can factor out, and you're going to have to bear with me on this one. If I factor out the 1 minus e to the minus j and omega naught tau rise, I just want you to listen to me. Or I can do it here. If I factor out e to the minus j and omega naught tau rise out of here, I'm going to have two terms, e to the minus j n omega naught tau, and then times e to the minus j n omega naught tau rise, right? Then I can factor out the 1 minus e to the j n omega naught tau out of these two terms, and I get 1, and it would be, because there's a minus sign, it's going to be minus e to the minus j. I'll just put down what they are. You can figure it out for yourself, but it's not hard. 1 minus e to the minus j n omega naught times tau rise, and then it's going to be 1 minus e to the minus j n omega naught tau. If you go ahead and do the multiplication on this, you see you get this. 1 times 1 is 1, right? This times this is going to be minus e to the j n omega naught tau rise. then this, pardon me, this times this is going to be minus e to the minus j and omega naught tau, and this times this is going to be plus that. You all see this? It works, trust me. That's all I'm trying to do. I have people asking me, go through the dividing this out. And say, oh, we'll take this quantity and divide it into that. And I'll put 1 there. And then, well, how? Because it goes into this quantity one time. How did you know that? I didn't know it. Don't worry about it. Especially if you're not, you had a long night writing papers and a little tired. You don't see things right away. You all agree with this class? Right? Somebody want to clue me what I'm going to do next? I'm going to break up these coefficients by half, right, and factor out the negative, and then I'm going to get this. Guys, I'm going to do it over here. I'll start on this board again. Does anybody know of a good dry erase marker that works on this thing? Because, I mean, the ones that we're ordering, they just don't do it. And I just wish they would put a whiteboard up. I mean, what is the deal with this thing? Is there some advantage to this I don't know about?
It matches the wall. It's literally just it looks good in pictures. It looks good to your students. Will pay money.
This is the worst board I've ever written on in my life. I'll take a chalkboard any day over this. This is absolutely the pits. I guess I'm complaining. I'm really commenting that I think they should look into this again, and I hope Dr. Nelm sees this. I guess most people don't use the board, huh? Do most of your profs use the board or not? What?
We had where the Dr. Hum used the projector, so they did it all on their own.
All right. Well, you can do that, but I'm. Hey, look, you go to big schools, all right? I mean, some of the best, Stanford, Harvard, MIT. I watch videos too, all right? Highly technical stuff where you got a million drawings, they're going to have projectors and stuff. When it comes down to the brass tacks of fundamental theory, it's almost always 3 chalkboards or a couple of sliding whiteboards. It's never done on an overhead projector, I can tell you that, at least as far as I know. Okay. Back to square one here. I have that. So now I have my Cn double prime equal to A over tau rise tau. All right. Sorry, T, pardon me. Tau rise times T. And then we have those terms, the 1 minus e to the minus j and omega naught tau rise and 1 minus e to the minus j and omega naught tau. And I'm going to factor out, as you rightly said, I'm going to factor out e to the minus j n omega naught, and then it's going to be tau rise over 2 and e to the minus j n omega naught tau over 2. Now I'll combine these in a second, but I want to make sure you see I've taken out those 2 values. What that leaves us with is this. Now I'm going to have e to the plus j n omega naught Jn omega naught tau rise over 2 here minus e to the minus Jn omega naught tau rise over 2. And I'm going to have e to the Jn omega naught tau over 2 minus e to the minus Jn omega naught tau over 2 here. And y'all know what I've done, right? I've simply factored this out for one reason, and only one reason. Somebody want to tell me what that reason was? Because I know you know it. Oh, I know you know it. You're just not saying because you said it the last time. You're awake. There you are. What did you? Euler's, yes. And Euler's identity says the sine of theta equals e to the j theta minus e to the minus j theta over 2j. Y'all get that? Now what do we have? We have e to the j, not theta, but n omega naught tau rise over 2, and e to the j n omega naught tau over 2, and then e to the minus j conversely, over not 2j, but just by themselves. So we put a 2j here, right? And now we come over here and we can say what this is really going to be 2 times j squared, because there's 2 of them that come out. And then I'm going to have the sine of n omega naught, n omega naught tau rise over 2 times the sine of n omega naught tau over 2, right? And I have that. Now, I basically made those into sine functions. Got me, class? You all see this? Can you see it in the far back, Randy? Okay. Now, that's Cn double prime. Please listen to this point I'm going to make. What is Cn double prime? I got there by taking 2 derivatives. That's what the double prime indicates. So that means it's our real Cn that we want, and it's times Jn omega naught squared, right? You all agree with that? Class? Can you got that on? All right. Now, yes?
We went from this and we split them up into halves.
We factored out this, right? If you factor out e to the minus Jn omega naught tau rise over 2, then you leave left here with e to the plus Jn omega naught tau rise over 2, right? And this would be e to the minus Jn omega naught tau rise over 2. And therefore, I can make that into a sine. The goal is make them simple trig functions. I mean, that's right, but I can't do anything with that. This I'm starting to do stuff with. Now, if this is the case, please, people, just watch this one point. You all see you have a j squared here, I have a j squared there. Do you agree with me? So, if you can ever get rid of j's, do it. That's the first thing. Next thing I'm going to do is divide by n omega naught squared, okay? I want to make sure everybody sees this. Do you understand this? Because my goal is to get C of n. That's the goal. So when I divide this over here, and I'm going to break it up on purpose as 2 terms, it's n omega naught and n omega naught, right? And now I've got C of n. Does anybody remember the next step? Some of you do, but you're not going to say, probably to spite me. Does anybody remember the next step? You're trying to make it nice, but there's one particular thing I'm going to do. I want to make a sinc function, all right? Because sinc functions are very useful functions to understand. Here's what happens. First, what is a sinc function? Well, the sinc, if I talk about this, of x that we define, and there are 2 things that are used to define a sinc function. So your very first thing, whenever you're reading and somebody says sinc of x or sinc of n omega naught tau over 2, find out what their definition is. The sinc function is actually that we're going to use as sine of x over x. There is another sinc function that has sinc of x as equal to sine of pi x over pi x. I just want you to understand they both have a very similar pattern, but the reason they put the pi x here and the pi here is so the zeros occur at integer values. That's the reason they do it. It's just for graphing purposes, not for analysis. Now, you all see that the argument here, that's what we need. We need the argument there. That would be this x, would be n. Yes?
Those 2e to the negative j and omega.
Yeah, I know. I didn't put them in. I'll put them in. Those didn't make it. You're right about that. We're going to see that that isn't really going to be a factor because we're after magnitude information. But you're right. You're absolutely right. My mistake. Now, what I'm going to do is this. Let me do this here. Okay. Now what I'm going to do is this. I need to make this argument look like this. You'll notice there's a tau rise here. Agreed? So I'm just going to take tau rise and put it right there. Now you'll notice there's also a 2. So if I divide top and bottom by 2, I get rid of one of those 2's and make this a 2. You all see that? Right? Now, for that one here, I need n omega naught t over, or tau over 2. That was tau rise. Well, I got the 2 right here in front of me. So I'll put that in. But now I need a tau, don't I? How am I going to get one? Well, I'm basically, that was tau rise there. I'm going to multiply, this is capital T, that's A. All right. What I'm going to do is multiply top and bottom by tau. And when I put the tau, it's in here. Can you all see this? This is the exact analysis I'm doing here is in the print or in the OneNote, and I posted this whole thing. You looked at it, right? Hopefully this will clear up any uncertainty you have. This is why we're doing it. We're getting it down to simple sinc functions. Now, you can see that this is a sinc function, and this is a sinc function, and that is a phase information. So now I can say that this basically is A times tau over T, and then it's going to be times the sinc, S-I-N-C, of n omega naught tau rise over 2 times the sinc function of n omega naught tau over 2. And all the phase information. Yes, you're right. Times e to the minus j n omega naught, and it's really tau plus tau rise, whole thing over 2. But that's my value of C of n, just C of n. Do you all agree with that? It's in the notes, but this is C of n. That's the coefficient of the Fourier, exponential Fourier series. Do you follow me on this, class? It's real important. Everybody has an appreciation for this. All right. Now, so far, so good. Couple of things that are going to come up, and this is the part you got to be attentive to. I don't want this in the standard exponential Fourier series for a reason, because we're trying to get this into something that can be used or understood as the input to a circuit at given harmonic frequencies. Remember, whenever we do circuit analysis at a constant frequency, we have a magnitude of something like 10 volts times cosine of omega naught t plus some phase angle. When we do the analysis, we go in the phasor domain and we just have the magnitude of the voltage at an angle. It's an assumed frequency. We want that form of a cosine, so keep that in mind. That won't do it, the exponential, or I should say the exponential series I had. That's the coefficient C of n for the exponential Fourier series. Please watch this stuff. It gets really important that you keep the track here. I'm going to do problems too. Now, you know, there are professors that do this very casually, quite fast, and they assume either students got it or not, and it's their problem. I know from past experience this causes a lot of grief. So I'm trying to alert you to this fact. It will cause you great amounts of grief if you're not attentive here. Remember what this Cn is for. It's for x of t being equal to the summation from n equals minus infinity to infinity of C of n times e to the j n omega naught t. That's the C of n. That's where that C of n goes for the rise time constant and the fall time. Now, what I'm going to do is say, do you agree that C of n is complex? It has a magnitude, it has a phase. Does everybody agree with that? So my first thing I'm going to do is say, I'll rewrite this as the summation n equals minus infinity to infinity of the magnitude of C of n, e to the j, and I'm just going to put angle of C of n for now, times e to the plus j n omega naught t. There's my first thing. I turn C of n into a magnitude and angle. Now, I'm going to take this series. My goal is to turn this into a cosine waveform. You're going to see how. But what I'm going to do, this is a doubly infinite series. It starts at minus infinity, goes to positive infinity. I'm going to break it up as such. I'm going to say that series is actually equal to the summation from n equals minus infinity to minus 1 of this, magnitude of C of n e to the j angle C of n, plus C0, and then plus the summation of n equals 1 to infinity of magnitude of C of n, e to the j angle of C of n, times e to the j, wait a second. Let me hold on for a second. Let me put the times e to the j and omega naught t there. I'm sorry, I didn't get it in. And then it's plus C0 plus this, and it's times e to the j and omega naught t. And the only thing I did is take this series and I broke it into a part that goes from minus infinity to minus 1. Then at 0, it's just C0. And then from 1 to infinity. Are you with me? How many know what I'm going to do next or have a good idea? I'm going to play a little trick. And this is the way it works. C of n here is equal to, technically, it's equal to 1 over t, the integral of some function x of t, times e to the minus j and omega naught t dt from minus infinity to infinity, right? You agree with that? Well, what is c of minus n equal to? Where's the place n occurs? Here, right? If it's minus n, it's that, isn't it? Do you all agree? Now hear me. What this really means to me is that c of n is equal to magnitude c of n, e to the j angle of c of n, and c of minus n is same magnitude as c of n, only the angle will be minus j, the angle of c of n. So what I'm really trying to tell you is this has a given angle, right? If you make it n minus, the angle just becomes negative. It's the conjugate of this. Do you all see this, class? And the reason is the sign flips there. And I can prove this in a couple different ways. That's the simplest way to see it. All right? Because that j n omega naught t is the phase. Now, you do have to integrate it out, but nevertheless, the sign will carry through. When I do that, what I can do is this. And I'm going to try to do it here. You don't have to write this part down. Let me just get to the bottom line on this one. Just watch, though. Please watch attentively. What I can do here is just make this series, instead of going from minus infinity to minus 1, I can go from minus 1, right, to minus infinity. Doesn't matter the order. I can do one other thing. Because n is minus, well, just make that plus and change this to minus n. But I know the magnitude of c of minus n is the same thing as c of n, so why even distinguish them? Just make it c of n. And this just flips the sign there, right? Now, I'm sorry, I didn't have the minus there. No, I don't need it right there. And yeah, because n is negative, then this becomes minus j and omega naught t. I'm trying to do it in one fell swoop. Do you all see that? All right, now here's the deal. I can combine these exponentials. I can combine these exponentials. Do you all see that? I can also put them both under in back of the same summation sign. So now I have the sum here, n equals 1 to infinity of magnitude of c of n here, and I'll factor that out. And then I'm going to have e to the minus j, and the quantity is n omega naught t, plus the phase angle of c of n, plus, and then here it's going to be e to the plus j n, plus j n omega naught t there, plus the phase angle of c of n. You all see that? I wanted to do it because of one particular thing that's true. Isn't the cosine of theta equal to e to the j theta plus e to the minus j theta over 2, right? It did another one of those things that it does all the time. It forgot itself. Yeah, I forgot it. You all see what I'm doing? I just took multiplied by 2. So what does that term right there become? just cosine of the exponential's argument. You all see that? And I'll write it out specifically. So now I can say that this is equal to, or my x of t is equal to C0. C0, by the way, is the DC, or the average value of the actual waveform over one period. That's all it is. There's nothing tricky about that, and you can't get that using derivatives. That's something you have to go back to the original waveform and calculate. C0 is just the average. I call it the DC value. It's that plus, and now it becomes a summation from n equals from n equals 1 to infinity. Now it's 2. All right, now just listen to me. That's magnitude. 2 times the magnitude of C of n, and then it's times cosine of n omega naught t plus the phase angle of C of n. And that's a very, very important thing to understand. X of t, after all is said and done, we can get the value of C of n if I know the rise time and tau in the period. I can get C of n exactly, right? And I can also do one other thing now. Because I've got that waveform, this is exact, by the way. Each one of these terms right here, that looks like something I can assume. If it's a linear system, I can feed just n equal 1 term into the input of a linear circuit and calculate the output. Let n equal 2, I feed that in, I can calculate the output, and so forth. Add up all the outputs plus the n equals 0 output, put C0 in there when the frequency is 0, and I can just find the output of any system using phasor analysis. Now, I'm going to do that later, but for this lecture, I'm not going to focus on that. I'm going to something that's more applicable right now. We'll get to that in a little bit. Next thing I'm going to do is take that, and I'm going to say that that C of n that I have here is very, very interesting. And here I need to do something. I know you're going to be mad at me for spending this much time doing it, but I need to go through the basics with you. This is a lecture that I like an hour and 15-minute lectures for this particular topic because it's seamless. Well, I'll leave that. I'm actually going to leave that here. And that's C of n. Just watch me here. Now, what we like to do is this. We're going to do two things. First thing we're going to do is say, normally when we take a waveform like this and we link it into the frequency domain, right? If we take any waveform and take it into the frequency domain, you get a function of frequency, right? Next of omega, correct? Then when you have that, you can say that if I could plot on this axis 20 times the log of the magnitude of x of omega versus omega, I could get some useful information. Do you all agree with that? What we're going to do is we're going to look at the magnitude of the coefficient of this cosine. By the way, somebody should have yelled at me. Yeah, there it is. It's a 2. See this coefficient? That's like V naught, right? I mean, it's some constant, but it varies with n. You with me? Now, what we're going to do is take a look at, because the cosine term itself just says where that frequency is operational. When n is 1, it's at omega naught. N equals 2, it's at 2 omega naught. We're looking at the actual spectral component. So what we do here, let me do it this way. The C of n is here, and I'm going to do something, and I'm going to take you through it right here. Now, if you pay attention to this, and I don't want to do it fast, I want you to appreciate what I'm going. You realize that n omega naught is discrete values, right? But we could look at how this behaves if n omega naught became just omega and swept the continuous frequency. What we would get is an envelope effect, all right? We would see, admittedly, we'd see the overall trend, and we could pick out specific frequencies. But if we let n omega naught just go to omega, so basically omega naught is going to be extremely small, and n is going to have a huge number of values. Just think of it that way. Then I can go in here, and I can say, and you don't have to write this down. I'll show you the one thing to write down in a second. This becomes just omega, and this would become omega. And now, there's a reason I did it that way. Now, what is omega? It's 2 pi f, right? So if I put in 2 pi f, now I'd get this. I would have simply pi f times that. Do you agree with me there? And this would be pi f tau. And that would be equal to the C of n. Now, I didn't do it here, but it would be 2 right here. This would be pi f times those two. And that would be now not C of n, but C of omega. All right? Now, that right there is very interesting because that's the coefficient of the cosine waveform that tells you what frequency you're at. So if we take this, and here's where the bottom line is on this one, and instead of plotting 20 times the log of x of omega, we plot on this axis 20 times the log of the magnitude of C of, now it's going to be of f, versus not omega but f, and this will be logarithmic. So if this is 10, this would be 100, this would be 1,000, and so forth. You know, you get the idea. This is a standard way of doing it. It's log there. The paper takes the log, and we plot 20 times the log of the magnitude C of f here. I want you to see what happens. When I take 20 times the log of the magnitude of this, first thing we get rid of is the phase, don't we, class? You agree with me? So now try to understand I'm plotting on that axis. So 20 times the log of the magnitude of that. Well, it's 2 times the magnitude of that times magnitude of C of n. That becomes this. It's going to be 20, just write this down, times the log of the magnitude of A tau over T. All right, that's the coefficient out in front. You can forget the phase. Then it's plus 20 times the log here of the magnitude of sine, and this is going to be pi f times tau, or tau rise. It doesn't matter. I'll put tau first in this case. Then it's going to be plus 20 times the log here of the magnitude of the sine of pi f tau rise. All right? That's what goes up here. Now, something very interesting about sinc functions that I'm going to have to spell out. Yeah.
Are those sync functions in the Brody plot? 20 log sine?
These sinc. I said sine probably. It's supposed to be a sinc. Those are sinc. What I did is take 20 times the log of this. They're sinc functions. Are you with me? Just hang in there. I'm trying to get this part of the lecture in. All right. Now, if we have this, here's the thing about a sinc function that's so unique. If I look at sine x versus x, I want to make sure you see it, which is the sinc function. Well, sine x over x, when x is small, is just 1. This is versus x. All right? Now, at pi, it's 0. Do you all see that? Sine of pi, sine of 100, it's 0. So if you find pi out here somewhere, it doesn't matter where it is, it's 0. It does this. And then at 2 pi, this will be 13 dB down, by the way, 13.2 dB down. And you can go to 3 pi and so forth. And it keeps dropping. Well, what happens is this asymptotically, the thing that's the envelope of that, the overall envelope, is proportional to 1 over x. And in general, the way they say this and do this is they say that if we have sine of x over x magnitude is about 1 for x small, whatever small means to you, and sine of x over x, and this is the envelope, goes to just 1 over the magnitude of x for x large. Now, you can try that, but that's the envelope. In fact, what really is happening with us, because we have discrete values of frequency, what we're going to see is at every omega naught, we're going to have these values, right? We're basically having that. But the envelope is the thing you're worried about, because that's worst case behavior. Do you all see what I'm talking about? You're always worried about worst case behavior. Now, when we plot that, follow me, it all starts right here. That's where it starts when omega is 0, isn't it, class? So the value that you always come in at is that. Right here, you're going to come in at 20 times the log of magnitude 2a times tau over t. By the way, tau over t is the duty cycle. And a 50% duty cycle would just be log of a times 20. Got to tell you one other thing. Almost always, when you're dealing with voltages or currents, they're going to do this in dB microvolts or dB microamps. So that means this. Just hear me on this one. This right here will be divided by 10 to the minus 6. Now, I'm not going to do it right now, but you follow me on this one, class? Because then that would be dB microvolts. You've already made it, everything in microvolts. All right? Where's the first point it breaks at? Well, what happens is where the first break frequency is, you all realize when this becomes like 1 over x, right? Then I have really 20 log of 1, which is 0, minus 20 log of x, right? And x in here is really going to be this. Follow me? Now, where does that happen? That happens when pi f tau equal 1, or when f is equal to 1 over pi tau. So first break frequency you always get is right here. Please just write this down. It's 1 over pi tau. I'll do a bunch of problems to make sure you see this. And it starts coming down. Sue me for being over. So it's minus 20 dB per decade right there. Where's the next break frequency? Just look. It's when what? Pi f tau rise, isn't it? And it's, yeah, pi f tau rise equals 1, or f is 1 over pi tau rise. This is the next break frequency. It's right here. It's 1 over pi tau rise, and then it starts breaking at minus 40 dB per decade from that on. I'm going to give you some simple problems with this to get you just thinking and probably form some questions. On Friday, I'm going to go through this. Yes?
Wouldn't that move the quiz to maybe Monday? Some of us have 2 tests.
How many have 2 tests? All right, we'll move to Monday. But I want you here, all right? And I want you to at least try some of these things, because I'm not going to do this twice, and this is a very important lecture.